Okay. First is, I'm not sure who is the first presentation.
I think so. Mahmoud is first.
Mahmoud, right? Okay, I will check.
Could you please check the list?
Okay, I check. Okay, today the first is Mahmoud. Are you ready? Hello, Mahmoud. Mahmoud, hello. Can you hear me?
If he is not ready, then I can present my one just to save the time.
Okay, I see. Salihu, you stay here?
Yeah.
Salihu. Okay, I start from Sakib. You ready?
Yes.
Yes, I'm ready.
Okay, if you're ready, you can share your screen and your start from your presentation.
Okay, thank you to giving me the first.
Okay.
Please disable the participant screen sharing. Let me share my screen.
Am I audible? Hello?
Yes, Mahmoud. Oraya, can you disable the restrictions to share the screen?
Okay.
I can't hear. Hello?
Mahmoud, you second. Okay.
Can you hear me? Hello?
Yeah, I hear you. I can hear you.
Okay, you can hear me?
Yeah. Okay, you can share again. Sakib.
Okay, let me share.
Okay, Sakib first and Mahmoud
But-
second,
but-
right?
but
Okay, and
I can't-
Salihu in the final. Okay.
I can't hear you.
You not hear me? Everyone, can you hear me?
Yes, can you hear me?
Yeah. It's clear.
Okay, cool.
Okay, you start after you in a second. Okay.
Okay.
Okay, Sakib, if you're ready, you can share screen.
Okay, so
Mahmoud is,
Okay.
Mahmoud is going to present. Mahmoud, present it, please. You are ready. Please present.
Okay. Let's start. Okay.
Okay, I should be the one to first present. I think
It's okay. You can start. You can start,
Okay.
Mahmoud. Don't worry. Okay.
Let me take photo video. Oh. Okay. Is it okay? Okay.
Your slide is not full screen, Mahmoud.
It's not full screen,
Yeah.
but from our end it seems full.
Can you click
Can you
maybe
see?
in the under
Okay, let me
right
stop
hand
sharing.
side
Let
and
me
share
stop
slide?
sharing and then share again. Just a
Okay.
moment. Okay. Okay. Thank you very much, Professor. And
Yeah, it's okay. You can start.
can you see it now?
Yeah.
Okay. Let me try to just trying to see. What's wrong? I want to expand it, but it seems to be. Yeah. The issue here is from my own end. I'm trying to. Oh. Really? Can you see it now? Hello, can you see it?
I see, but not full screen.
Not full screen.
Yeah.
Okay, let me try to make it so. Just a moment, please. It seems to give me kind of like, I'm not sure why. Oh, oh, really? Yeah, the slides is not showing full screen online.
Somebody see you online full screen?
Yeah, they cannot see me online full screen. That's the problem.
Yes, you can see online full screen.
There's somebody should check so that you can get started.
Where is
Things that yes, that's what I'm trying to fix here, but I'm wondering why. Yeah, but many people online cannot see it this way, the way you see it. That's the issue. But here, let's try to see, not duplicate, swap, slide through. I don't know. Can you see it online?
okay? Oh, opposite, yeah. Yeah. Yeah.
Okay, this is okay, transpose. Wow, that's interesting. Okay, good afternoon, everyone. Good afternoon, Professor.
Yeah.
Okay. Good afternoon, everyone. Good afternoon, Professor. Good afternoon, all the participants here in the lab and those online. So my name is Mr. Mahmoud Muhammad Yaya, and today I would like to give a seminar presentation of our fixed point lab. And the title of this talk is Approaching Gradient-Based Methods via Non-Monotone Line Search Scheme or Algorithms. So the outline of this talk as follows. Number one, I will start with a brief introduction. I hope within this brief introduction of 2 to 3 slides, you'll be able to understand what I'm trying to portray to you. And then followed by a brief discussion about a non-monotone conjugate gradient algorithm with some brief description of how it can be applied to solve various real-world problems. So let's begin with the introduction. So the question that we can simply ask ourselves is, what is a gradient-based method? Because you see from the title, it says that gradient-based methods via non-monotone line search. So as a curious person who is listening to this presentation might tend to ask himself, what is that? What is this all about? So let's briefly talk about this in an intuitive sense. So suppose, for example, we have a function. We are given just a function. Let's assume for this sake of starting point that this function, we don't know what it is, but we just know that it is a function. And it simply maps element from a set A to another element to another set, say B. But this set is actually could mean a lot of things depending on what you are trying to solve or depending on what you are trying to model. So let's, for the sake of simplicity, say that this set is simply Rn, which is n-dimensional Euclidean space. And the B is simply, let's say, just real numbers for simplicity, but you can take it to be infinite dimensional space, H to H, and so on and so forth. So the idea here is, assume that you have an oracle. So the question is, what is an oracle? You can think of an oracle is just simply like a black box that you don't know what it is, but you are just giving an oracle. But within this oracle, it's kind of like giving you some information that you need about this function F. But this function that you have here is a function that you hope to, for example, assumed maybe you model this function as a problem of maybe trying to maximize, for example, the profit you gain in your business, or maybe you model it as just a problem of maybe trying to minimize the set of risks that you might involve in a business. So let us assume for the sake of simplicity here that we are trying to minimize this function. And this function is going to give us, this oracle is going to give us two informations about this function. So what are those informations? So the first information that is oracle that we don't know about for the starting point here is just the f, and of course the gradient of f. This is actually a gradient. We say gradient. Obviously, here we are trying to say that the derivative of f in the in Rn, for example. But normally, if you are talking about from R to R, we are just talking about the derivative directly. So now we are trying to say that this oracle is going to give us these two information, the function and the gradient value. So if this oracle is all it can do is just to give us this information, we call this kind of oracles first order methods. I'll give an example of these kind of methods in the subsequent lines of presentation. And then secondly, for example, if in addition to these two information that we have, that this oracle is giving us, let's say the function and the gradient, is also giving us an additional information about f, that probably we need those information in order to be able to minimize the function. So let's say that additional information is the Hessian, which is basically the second derivative of the function itself. This kind of method that gives us this kind of information, the function value, the gradient, and the Hessians, we normally call them second order methods. So I'll give an additional example of this kind of second order method in the subsequent lines. So the next question that you need to ask yourself is, of course, in the title, it says gradient-based methods. And in addition, it says something about line search. So what is that line search? You will be curious to ask. So we can intuitively describe this in the following lines. For example, this oracle, it happens to give us this information of f and the gradient of f, coupled with the Hessian by following a particular pattern. And this pattern is, say, for example, you start from, let's say, a point, let's say x naught, and in an iterative fashion, you are able to find the next point using this line that we are seeing here. So this line, if you look at it, obviously we have kind of like a sequence, right? So you have xk plus 1 equals to xk. So at the current point, you try to evaluate it by using the previous information that you know of. But in addition to that, you have some terms that we are seeing, kind of like magic terms. So the first one is alpha k, and the second one is the gradient of f of x at that point. So this alpha k is normally called a step length. Of course, maybe people call it different names in different situations, but from this perspective, you can simply call it a step length, for example. But how can you be able to find this step length? So people used to find this step length in different approaches. And one of the approaches people used to find is called line search approach, which I will talk about later. And this kind of a method or an oracle that try to find the next point using this kind of approach is what we call gradient descent method. So it has a lot of names. People call it steepest descent. Some people call it gradient descent. So it depends on kind of like the school where you are trying to work. And in addition to that, for example, in another example of the second oracle that use the second information of the Hessian, of the function, which is Hessian, which we simply call the second order method, is called what you call Newton's method. So this is actually how the step of finding the next point in a Newton's method looks like. And actually here we call it not necessarily Newton, but people call it damped Newton's method. So it is a Newton's method that has an additional term, which is alpha. And this alpha k could either be 1 or it could be evaluated using line search. So when the alpha k is strictly equals to 1, people call this strictly Newton's method. So it's kind of using the second information of the function, which basically is the Hessian here, multiplied by the gradient. So, but if the alpha is obviously used or evaluated using line search, people call this kind of methods damped Newton's method. It has the reason, or people have reason why they try to approach it this way. We'll talk about this later. So now we know in an intuitive sense what a line search is. And we have some few examples of these first order methods and second order methods. So let's go back history a bit. What is a gradient method? So this gradient method, or steepest descent, was actually coined by this French mathematician in 1847. So you can just think about this idea of just rolling a ball down a hill, or you start from somewhere, maybe you start at a point and then you just drop the ball and then it keeps rolling down, as you can see in this description here. Where this figure here is kind of like the gradient vectors. So now let's move on to the mathematical description of this line search that we are trying to talk about. So we have in a general setting, for example, we have two ways of finding this line search. So people used to say that we have exact line search and inexact line search. So the exact line search is actually a good idea, kind of like an optimal alpha that you almost always want to have, kind of like a state, but it's the optimal one that you need to have or you need to evaluate at every iteration. So this sounds like a best way to find it. If you can be able to find it, you just have no issue. Okay, your function is the step that you are trying to move downwards is going to move with that expected step or optimal value that you need to find as alpha key. But it turns out that it has some issues when you are dealing with maybe high dimensional problems or problems that have high number of functions, high variables, for example. So it is a bit computationally expensive. That's one of its drawbacks, but it is actually a cool idea if you can have it. So to avoid this kind of issue of computational intractability of this kind of computation of line search or exact line search, people try to say, okay, why can't we just maybe just have a simple one? Since I cannot get optimal, then why can't I have an approximate value that can be able to help me find or move the step that I want? So one example of these approaches is called inexact line search. And this inexact line search, you can think of it as just saying, okay, the function is trying to monotonically decrease, okay, at a given point, f of x, k plus 1, for example, the function, let's say it starts from somewhere, but the inexact line search is basically describing the monotonic decrement of the function at every point. So you are trying to find the best alpha that will lead to decrement of the function value. So this actually is a prepared approach people try to use. In fact, all the non-line search that you will see in the subsequent slides kind of like being derived in one way or the other from this inexact approach that you are seeing here. So now, having known this classification, of course, people have constant line search, line search approach, okay, and people have other variations, but in kind of like a general setting, we have these two classes. So now let's move on to the variations of this inexact line search. So one of the well-known variation of it is called a unusual line search, which is basically described like this. And as I mentioned earlier, this is basically a variation of this that we have in this fourth cycle. So it has kind of like an additional terms here, some bunch of constants and some bunch of values here. So here we have sigma, we have alpha, we have, so all the values or all the alpha that we are trying to find, we are trying to find it in such a way that this condition or this inequality is satisfied. So this line that we are seeing here is kind of describing one of the approaches that people incorporate the unusual line search, normally called backtracking approach. So now the question that we need to ask ourselves here is, okay, this is quite good. Okay, so what is the problem? Why do I need something else? Why do I need, since this is monotonic, okay, so it's going down, why do I need another thing? Why is it important for me to be able to consider another variation of this? So I have a simple example here, which is kind of like a 2D representation of a Rosenbrock function. This is actually a non-convex function, classical formulated like this. So example of this, for example, let's assume we try to solve this problem or this function that has two variables using Newton's method and damped Newton's method. So if we can represent this function with the contour lines like this. So here, if you look at it here, this is counter plot of the function itself, and it's kind of like describing where or how this approach of Newton's method took in trying to find the minimum of the function. So the minimizer here. So if you look at it very closely here, we can simply see that for the damped Newton's method, which actually uses the unusual line search that we are seeing here, it's kind of like starting from a point here. So this starting point is actually kind of like the starting point of both approaches. Let's say the damped Newton's method and the Newton's method. And the starting point is actually minus 1/10, 1/10. So it's far away from the minimizer. And you can quickly see that the minimizer, by just simply looking at the function, is simply 1, 1, right? So let's say we start somewhere far away, let's say minus 1/10, 1/10. So the Newton's method using the visual line search is actually moving following these patterns, which is kind of like this one in this reddish light. So it's moving towards the minimizer here, which is 1,1. And if you look at it very closely, it seems like these steps that it tries to follow a kind of like a curved narrow valley that will lead to the minimizer. So it's kind of like enforcing this idea of monotonic decrement of the function towards the minimizer. But if you look at the damped Newton's method, which actually doesn't use this measure line search at all, it just takes the constant step, which is alpha equals to 1. So it's moving like this. So first it starts like this, and then just shoot and then move continuously. So just the step, I think they are less than, of course, the time it took the Newton's method with line and measure to go to the minimizer. In addition to this information, let's look at again maybe the function value with respect to the iterations here. So if you look at it very closely, the iterations is on the x-axis, and the iteration is on the x-axis, and the function values is on the y-axis. So the one in black here is describing the movement of the function, right? When we use the damped Newton's method that has alpha k equals to 1 all through the iteration. While the other one is the Newton's method is the one that doesn't have line search at all, while the damped Newton's method is what uses the measure line search. So if you look at it very closely, you see that the damped Newton's method is kind of monotonically decreasing, right? But it has some issues, obviously, from what you can see here, based on maybe the number of iterations that it took to go to the minimizer. But if you look at the Newton's method that has a constant step, which is equals to 1, it's kind of moving in a non-monotonic pattern. Okay, so it's first start and then it's move up, down, and so on. But it has an advantage in the sense that it has least number of iterations for it to be able to go to the minimizer. So this idea is actually what motivated people to talk about formulating or transforming this measure line search to what people call non-monotone line search, which is basically described here. So the function value here is kind of like taking the maximum here of the previous function value that you took over a given interval, for example, and all of these terms. So obviously here, if this m of k is equal to 0, we are just strictly going back to original formulation of the previous measure lines. So now, having a glimpse of this idea of non-monotone line search, let's briefly talk about how can we incorporate this non-monotone line search, or what is the advantage of incorporating this non-monotone line search to one of the line search or one of the gradient-based methods, for example, the conjugate gradient methods and others. But in this case, I did not use the conjugate gradient method, but for the subsequent slides, let's look at how can we incorporate this idea into the context of non-monotone lines, non-conjugate gradient. And in addition to that, there are variations of this non-monotone line search. As you can see, this is kind of like an old paper in 1986. So people try to come up with different variations of this formulation, as you will see in the next slides. So conjugate gradient method with non-monotone line search. So before I talked about that, let's say, for example, we have a problem to solve, because you cannot say we have an algorithm without knowing what we want to use the algorithm for. So assuming we have like kind of an algebraic equation, which obviously everyone knows about. So, back in your school, you can be able to say, okay, I can be able to factorize this equation number 1 into the product of 2 terms, which is an easy thing to do, obviously. However, what if we want to do that for a matrix? You have a matrix, you want to just decompose this into 2 products of 2 matrices. Can it be done easily? And why do I need to even do it to begin with? So the motivation of doing it here, you can have it like this, obviously. So the motivation of doing it comes from actually the application of this idea. Okay, so for example, you have a situation whereby people have kind of, this is one of the applications, which is called clustering actually. So the idea here is you have a bunch of information, for example, in Facebook, okay, a social media network. So you have a group of people, different groups have different interests. So you will join the group based on your interests and based on what you want to do in that group, or based on the class of people that you have. Maybe in your school or school, you have a group of friends that have something in common. So there is this form of grouping. And the idea of grouping here is, let's say we need to group those people based on their interests, right? So what Facebook does, in a simplistic sense, is kind of like having a graph, and each group is kind of being linked, or each person is kind of linked to the other person based on some interests that they have in common. Another application is in the context of recommender system, whereby, for example, in Amazon, you have, okay, you used to go Amazon and buy textbooks or buy stuffs and so on and so forth. But normally, if you go there as somebody who used to buy things, you tend to have an interest in maybe rating some product that you buy. For example, you buy textbooks this time around, and then you say, okay, this book is interesting, I want to give a rating about it. And since the rating is normally from 1 to 5, so you can decide to give a given rating for a given product that you buy. But you might not be able to do this all the time, okay? So sometimes you say, oh, I'm lazy, I cannot be able to do it. So why can't I just forget about this this time around, I cannot do it. So the idea here is, okay, so those kind of situations whereby you did not give the ratings, how can we be able to, as a company, for example, how can they be able to predict what is the possible rating that you give to a given product that you not rate in the initial sense? So this brings about kind of like formulating all these ratings in a matrix format, which incorporates the ratings values that you have or that people did over the products that they are trying to sell, and simply splitting this or decomposing this matrix, huge matrix, into two matrices that can be computed. They can be able to obviously predict what is the possible rating that is missing in the previous step. So this is the idea here. And you can think of this or apply this in the context of face dissection, whereby the idea is to try to find some information about a face, maybe the eyes, the nose, and so on and so forth. So each and every individual has some special features that one can be able to detect or see. As a person, you can be able to say that this person is having some features that I can easily use and understand about him or describe him. So the idea here is, if you represent those kind of information in metrics, you can be able to, separate or decompose those kind of informations and use them in a subsequent pattern or whatever sense you want to use it for. So now let's talk about the formulation of this. Now we know the motivation. It has some application, it has some usefulness in one way or the other. So now, how can we formulate this in mathematical sense to be able to solve it? So let's have this kind of representation. So the idea here is, let's say X is simply a real and non-negative matrices, which is an M by M matrix. So the problem is called non-negative matrix factorization, whereby you try to find two matrices that can be able to, or that you can simply be approximating, that their products will simply approximate the original matrix. And this can easily be represented using this equation number 3, whereby you're trying to minimize this norm of these two matrices, this matrix, and just kind of like try to say, you try to find the minimum, you try to minimize the difference of these two products. Where this R is kind of like the rank, which kind of describe the dimension of how you want to split those W and H into. So this can easily be represented as what people call unconstant optimization, whereby you are trying to minimize a function f of x, where this x is coming from Rn. So this is a simplistic representation of it, but you can be able to reformulate this into different patterns, maybe sum of functions, 1 or 2 or whatever, depending on what you want to do, or depending on the model that we are trying to solve, or depending on the kind of algorithm we are trying to use it for. So this f is assumed to be twice continuously differentiable. So now let's talk about the approaches to solve this problem. Before, if you can remember, we talked about this kind of like this step number 5, but in another setting. So here we have kind of like xk equals to alpha k, an additional term, which is dk. So this dk is called the search direction, which kind of like differentiates this kind of various formulations of this kind of first order algorithms and second order as well. And we have a simple example of this step or alpha, which we call admixture line search, which I talked about earlier. And in addition to that, we have a variation of non-monotone line search. So if you can remember earlier, I said there are a lot of variations of this non-monotone line search described earlier. And one of them is actually proposed by this researcher, Masoud. And he described this in this equation number 6. So this is kind of like converse combination of the max value and the current function value. So assume that you try to say you try to find the maximum, sequence of function values. But at the same time, even though you have the max, but why can't we, let's say, have an information about the function value at that current point? So this is kind of like the idea he tried to formulate here. And this eta k is kind of like trying to say, converse combination. And when k obviously is equals to 0, we are just strictly going back to the previous setting of our measure. But if it is bigger than 1, you have it in another sense. So the idea, although I talked about the usefulness, at least in an intuitive sense, but it has some advantages actually. Number one, this idea actually helps in or improves the possibility of getting the global minimizer of the function model or global optimum per se. And then it also has the advantage of possibly improving the convergence speed, because if you can remember the number of iterations of the number of these Newton's method with just constant state turns out to be very low, or kind of like 7 or 10, something like that. And then from some experimentation, people turns out to find that using this kind of non-monotone line strategy for highly nonlinear problems strictly, it has a lot of usefulness, has a lot of numerical advantages. So now, what about the eta k? So one of the idea here is how can we be able to formulate this eta k? So there are some works that try to formulate this. The initial paper used this first formulation here that we have, and the second formulation was formulated by another researcher, which is, I think, the Kevin Abini, who is the advisor of this Masood. And in this work that I'm trying to talk about, the formulation of this is stated in this equation number 6 third. So the idea here is, if you look at these two formulations, the first two formulations doesn't have any information about the function model, and based on this description here, they tend to have some issues one way or the other. The first one, which is the blue, turns out to just divert to some extent, we can put it like that. And then for the other one, is kind of starting fast, but then kind of becomes or stuck somewhere. And then obviously from what we can see here, we cannot clearly describe that, or cannot clearly say that those formulations uses the function value in order to solve this problem. So this is kind of like a description of this f of x, the steps or the approach in trying to show the advantage of eta k when trying to solve this f of x function that has x from R to R24. So now let's move on to the strategies for initialization of alpha k. So the alpha k, as we mentioned, is the initial, the step, it's kind of like a step. But how can we initialize it? One of the shortcomings, or one of the disadvantages of a conjugate gated method in a classical sense, is that it has some issues with initialization of this alpha. So in this work, they try to say, okay, why can't we formulate this idea, or why can't we formulate this alpha k in such a way that it took some information about the gradient, and as well as the step between the points, let's say sk plus 1 minus xk. So they formulated their idea here. And the next point, or the next thing that you need to know, or we need to know here, is the search direction, which is simply formulated for CG in general sense in this equation number 8. And there are a lot of variations of this beta k, which kind of like differentiate one formulation over the others. And the formulation mentioned or used in this presentation is the one proposed in this number 9, which is basically some constant multiplied by the norm of gradient divided by the norm of the previous directions. And the direction, one of the properties or one of the requirements is that it should be descent, which basically means that this condition needs to be satisfied. So we have the formulation or the schematic pattern of this algorithm, which has the following steps. It had the inputs, and then it has some steps. So the most important part of this are these 4 parameters: beta, dk, and eta k, and alpha naught, which are the ones formulated in this work. And we have some convergence results that describe this So actually the convergence here are based on some assumptions coupled with the idea here, coupled with, of course, the line search proposed. And these are the assumptions. And this is the lemma, which describes, first of all, the distance property, the boundedness of the direction, coupled with the well-posedness of the line search used here. And lastly is the theorem, which kind of like describe that this from this algorithm or this sequence of points that we are trying to use converges to some stationary points. And based on this work, the convergence actually is done without the assumption of the grade of the, of the convexity property. But one thing that we need to understand here is the convergence is not the global convergence that we people maybe in another area talked about. The convergence is basically towards the stationary points, obviously. So since we are assuming non-convexity at all. So let's move on to numerical part. So in the numerical segment, there are some description about the numerical because first of all, the dimensions used start from 2 to 5 million dimension. So they are kind of like a huge experimentation done in order to see what's the usefulness of this non-monotone line set when compared to other variations. So here, this is actually done using what people normally use in this area called what the normally people call dollar amount performance profile, which basically try to describe or try to make comparison between different algorithms or solvers. And based on these plots, we have the variations of these line search, the line search with BB, which is basically the Brazilian Boeing, the line search with non-monotone approach, and the one proposed here and some variations listed here. So this is based on function volume. And the one proposed in this discussion is the one that is at the top, which describes how robust this formulation is as compared to others, because the one that has the topped the graph, okay, to the right is the one that we can say is more robust. So the other metric used is the graded evaluation, which also shows some, performance. And the last one is based on CPU time, which is also very useful here. So in conclusion, we talked about an improved variation of this non-monotone line search, and then a new initialization approach for this CG algorithm is also, introduced here. And the new proposal of this conjugate gradient parameter is also described. And last but not the least is the, performance is tested on some, millions of dimensions of problems that are large scale. And normally those kind of test problems can be found in KMUTT library. So this talk is actually a paper that was first submitted in ANURIF's 34th, which is a very big machine learning conference that was discussed. I think it was done in Vancouver, 2021. Thank you very much.
Okay, any question or suggestion?
A question or comment or whatever,
Yeah.
please, the door is open.
Okay. May I ask a question?
Okay, I cannot hear you online, but I can hear you since we are in the same room. Okay, go on.
Okay, thank you very much, Dr. Muhammad, for this wonderful talk. I would like to ask you about
Okay.
before going into because of your presentation, you mentioned that you observe needs of because that is very, very important. Considering so, and you also stated that the function is not necessarily infinite.
Yes.
Okay. So that is to say we are looking for local either.
I'm looking for stationary points, not necessarily minimizer. Of course, local, but stationary points. Yes, yes.
So it could be a minimizer certain point. from my
Yes, yes, yes. But the theory of course I did not show it here, but the theory in fact from the original work, the theory shows that those points are not maximizers for sure. But they can of course be saddle points. That's also true. Yes.
Yes. So now normally the idea of that the ensure the function value is decreased. That is to say, by the time you reach the point where the gradient goes to zero, so the gradient
Where is Professor Point? He just left now.
Not necessarily.
Left. Now,
If the function is monotone,
he's not coming back.
yes, you can yes, you can think of it like that. Yes, yes. Exactly.
So this one is not going to recommend, but it will go anyway. That is going to minus.
But you have to understand one thing here. It's not saying that it is going to be maximum all the time. We are just trying to say, okay, let me talk about the maximum over a given plus, let's say over a given interval, small interval. Okay, so you are not strictly, yes, you are not strict. Yes, we are not going to say, oh, you are not saying strictly that you are taking the maximum over the whole function or over the whole points that you pass through. Okay.
Normally, what's local meaning is as far as like creating concerned, given a starting point, for example, say epsilon, then within each of the stationary points, closer epsilon. That major target of calculating method as far as local meaning is concerned.
Yes, because yes, I understand your point because we are trying to minimize it. We are trying to use those points to be able to minimize the function. So of course, we are just trying to say, okay, let me just try to move towards the function that points that will lead me to the decrement of the function value, obviously. So what's the question, please?
Yes, my point here is now, how do you intend to differentiate between minimum values of minimizing particular function and then demand like that regard? Because I can see in your application you consider minimizing the function.
Yes.
So then this kind of algorithm is not working on minimization program unless the assumption is it's assigned.
Yes. So one thing that you need to understand for the application part, the formulation of the application is actually a non-convex problem. But in the implementation, what we try to do, or what people try to do, because I'm not the one who first formulated the model, so they try to, structure the problem or like kind of rewrite the problem into two easily computable convex problems. So the pattern of computing or solving this model is actually a kind of like an alternative fashion. So first you kind of like fix the first matrix, let's say W, and then you try to minimize over H, for example. And then in alternative fashion, you fix the previous one that you minimize, and then you minimize the other one. So I did not describe the algorithm here for the because I did not talk about the application in the discussion. But actually, this is how the pattern works. Maybe after this presentation, I will show you how the algorithm looks like. So any question or comments?
Okay, if no any question, thank you for nice presentation, Mahmoud.
Okay, thank you everyone.
Okay, can you
for
stop
listening.
share
Bye-bye.
screen? Okay, thank you so much. Next presenter is Salihu. You stay here. You ready?
Yes, I'm ready.
Yeah, okay. If you're ready, you can share your screen and let's start.
Ni lokacin wannan din ya wuce ya zan yi ne. Lokacin da na sa Zoom din.
Ka shiga za ka yi, ba kai za ka shiga za ka yi.
Ni ba zan yi da wancan abun ba. Okay. Hello, can you hear me? Head.
You cannot share screen.
Oh no. Can you see my screen?
Yeah, I see. You can full screen mode.
Okay.
Okay.
Okay, good afternoon, everyone. My name is Nasir Salihu. I'm here this afternoon presenting our joint work on this topic, the global convergence of a spectral R-mel conjugate gradient method for unconstrained optimization with application to robotic model and image recovery. This is a joint work with my advisor, Professor Pumkam Am, which is just published recently at +1 journal. These are the outline of my presentation. In this work, we try to look at an unconstrained optimization, meaning that it is a type of problem that the search space is not restricted, whereby the functions is a mapping from Rn to R. This function, we assume that is smooth. The major motivation behind choice of this type of problem is that the problem is widely used in science, engineering, economics, and industry. For instance, in robotic model and image reconstruction problem. If you have an image that is damaged or corrupted by some noise, we want to recover the image back. So in order to do that, our main interest is to find the minimizer of a given function in such that the function value decreases at each iteration we took. And we assume that the x star here is a stationary point, meaning that the gradient is equal to 0. The strategy for moving from one iterate to the next iterate distinguishes most of the iterative methods. For instance, in steepest descent method, the strategy where we used to obtain one iterate differentiates steepest descent method from Newton method. So generally, iterative methods use this relationship too in order to get the new point, where alpha k here is a step size and dk is a search direction. And some algorithms obtain this alpha k exactly, meaning that they conduct one-dimensional minimization at each iteration in order to get the value of the function reduced. This is normally costly because if the variables involved in the problem is very large, this is impractical. It's not possible to do so because at each iteration, you need to do one-dimensional minimization. So this relationship is called exact line search. Based on this, Wolf proposed the following inexact line search that approximates the step size such that it gives reduction in the value of the objective function at each iteration. The relation 3 is what we call Armijo line search. What these two relationships normally does is that they ensure that we do not take much time. We do not take, the step we took is proportional to the decrease in the value of the objective function. And these relationships are required in order to show global convergence or convergence in general of some CG methods, while others require 5 in order to be convergent. The search direction dk is such that it descends, meaning that dk transpose dk is less than 0 or sufficient descent when we have dk transpose dk is less than psi, the norm of dk square. The main objective of our work is to obtain a new parameter, that is a new conjugate gradient parameter from such direction. One of the main advantages of this formulation is that it ensures sufficient descent without use of line search. Secondly, we show that the lines, that is, this direction is sufficiently descent independent of any line search. We also show that the method converges globally. And the last one, we implement the algorithm on some application like a robotic model and image reconstruction problem. There are various beta case in literature. That is the value of CG parameter called beta case. These are some earlier beta case proposed by HS, that is Estin and Stiffet, PRP, Polak, Riberia, Poliak, and Liu and Story. These parameters are assumed to be the best CG parameters numerically. While the second set, there is some echoes in the, while the second set of parameters are believed to be converge globally, they have a good global convergence properties, not like the first one in the first group. So naturally, there are some research going on in order to enhance the behavior of CG parameters in these two categories. Based on this, Rivery et al. In 2012 proposed a CG parameter, which is a modification of PRP parameter this. By changing this GK to DK, they obtain this new beta K parameter. Well, in showing the convergence property of this parameter, they assume that this relationship holds, which is numerically expensive, and sometimes this dk transpose dk in the middle may not be positive. Based on that, I propose this relationship 9. There is echo. Please, can you hear him? There is echo.
Echo?
Yeah.
No, it's okay. Maybe it's from your side, but we can hear you.
Oh, okay. Okay, so I modify the parameter in A to have this in order to have a very good global, a very good convergence property. So we now observe that it is at most cases that we must use this relationship in order to have a convergence property, the good convergence properties of this beta K are met. Based on that, we try to modify the search direction. Before then, the restriction given by die implies that beta K army will look like this. And this relationship is the most important relationship that is required in order to show the convergence of army method. So we now observe that without these conditions attached by die, we can still have the convergence of beta K army by scaling the search direction with some scaling parameter theta K. The essence of this scale is to remove the condition attached to beta K army in showing the convergence of the method. So this parameter was first proposed by Bagin and Martinez in 1997, where they incorporated spectral parameter into CG direction in order to enhance the convergence property of the method. So the next thing is we'll look at the methodology and formulation of our new method. Actually, we obtain our new spectral parameter by multiplying, that is, we multiply GK transpose DK to the search direction given by 10. When we do so, we obtain GK transpose DK is equal to some parameter theta. We obtain something of this nature, whereby if you apply Cauchy-Schwarz inequality, we have this. So when we observe this very well, we see that this is equivalent to saying that the new beta K, which we are about to obtain, is sufficiently decent, irrespective or independent of any line search. When we take our new parameter, that is our new theta parameter, to be like this, we see that we obtain our sufficient distance 11 easily. Without loss of generality, we can now say that our new theta K is given by this. Based on this formulation, we can easily see that we obtain the sufficient distance property, which is one of the backbone of CG method without line search consideration, meaning that we can use any line search in the numerical analysis of our new method. And if you observe closely, when theta K is equals to 1, we are returning to classical CG. If theta K here is equals to 1, we are definitely returning to classical CG direction. This is the algorithm we use in obtaining the numerical experimentation of the work. Some theoretical and numerical results obtained. We make some assumption in order to show that the algorithm is convergence. One of such assumptions is that we assume that the function is bounded below and we have Lipschitz continuity of the gradients of the function. So in order to show the convergence of our new method, we take the norm of the search direction. After taking the norm of the search direction, we have some claim before that the search direction is bounded. In order to show the boundaries of the search direction, we multiply the search direction dk. No, we take the norm first. After taking the norm, we expand. Then we substitute the value of theta K and beta K respectively. After the substitution, after some simplification, we obtain this, which shows that theta K is bounded by this parameter. When we set this parameter to be equals to P, easily we can see that the search direction is bounded by P. So if we square both sides of the sufficient descent condition given above, then we have this. So easily with this, we take the summation on both sides, we have this, which shows that it is a contradiction with what we can normally call Zhao-Tenji condition in CG analysis. So this is the convergence property of the new method. What this is just saying is that irrespective of our initial points, we can easily show that the algorithm reach a stationary point. These are some numerical results from the paper, whereby we compare our RMIL version with other RMIL versions of beta came. So we can easily observe that from this performance profile introduced by Dolan in order to show the performance of numerical methods, that the method that stay on, this is a probability whereby the method that stay longer on this part of the graph is the best method. So easily, based on number of iteration and CPU time, we can easily see that our new proposed method, which we call new spectral RMIL method, stay longer than other versions of RMIL methods and happen to be the best method in about 68% of the test problems solved at hand. Similarly, based on number of iteration, we have almost the same result. And our new method is able to solve about 88% of the whole test function used in the course of this experimentation. As we said earlier, that we are going to apply our algorithm in order to solve arm robotic model problem. First of all, motion control problem involve an actuator or a motor and end effector, which is given by these pictures here. The actuator is a device that allows for the precise control of position, velocity, and acceleration of a robot arm, meaning that it's the one that allows the robot to move, while end effector is the one that allows the robots to interact with the environment. So combining these two devices, the robot can easily move easily. Next thing is that the problem can be formulated as an unconstrained optimization problem in form of 21, whereby M theta stands for the kinetic model at the position level of the planar robot, which we want to actually see the level of difference between the actual end effector model given by 22 and the one we will obtain with our algorithm in order to trace the end effector and see the error, whether the algorithm is able to trace it effectively with a minimum error. In order to do so, we use our algorithm and solve this problem. Solve the minimized problem above. That is the minimization problem given by, where is it? Minimization problem given by this. After we solve the problem, this is the diagram, or this is the pictorial of the actual trajectory, while this is the form of the arm robotic model that we want to trace. So we can see that our algorithm is able to trace it very well with minimum error, whereby the one in blue is the desired path and the actual trajectory is the one in red. So the end effector of our new method shows by diagram A and B. And this is the error recorded on the course of tracing at the y-axis and x-axis respectively. We can observe that we have a minimum error between 10 to the power of -5 to -6 on both axes. Then the second part of our application, we use our algorithm in order to solve image reconstruction problem. Image reconstruction or image recovery is a process of estimating original or clean images from noisy or corrupted images, which is as a result of impulse noise or camera misfocus or motion blur. These are the main causes of causes of image to be damaged. In order to recover the original image, this is a huge or a very big task that requires some sophisticated algorithm in order to recover the image back. So this problem is widely come up in engineering sciences and health. In order to recover a damaged image, we need this formulation. That is, we need this minimization problem given by this. If we denote the image, that is the true image by X, with index on both row and column with M by N physics, which is given by W. Suppose that we denote the detected set of indices of noisy pixel by K, given by this. Then to restore the noisy pixels in the second stage, we minimize this function, where this denote the age preserving function that defined by this. And this is the set of neighbors. In each pixels, there are some pixels in the neighboring pixels. So this, we denote that by this. So after we conduct the experimentation based on 3 metrics, that is a CPU, based on CPU time of the 4 algorithms, irrespective, with respect to our own algorithm, you have the following. So we use 2 buildings in our university in order to carry out the experimentation, whereby we corrupt the building with 30%, 80%, and 50% noise. After we do the numerical simulation, we observe that our algorithm has less number of CPU compared to other algorithms when we have 30% noise. Similarly, when we have 80% noise, our algorithm happen to have less number of our CPU time compared to others. So also, but in 80% noise, we can observe that other algorithms perform better than our own. Similarly, in the second picture that we use for the formulation, that is the building we use for the formulation, our algorithms happen to perform poor based on CPU time, but at 50, the same thing. Then the last one, when the noise is 80%, our algorithm perform better. For the second metric we use, that is based on this error. So we have the number of errors compared to other methods we are comparing with. If you observe, you can see that our algorithm perform better than other algorithms when the noise is 30%, 80%, and 50% respectively. So also for the second building. In conclusion of this work, so this picture is not clearer, but it's just peak signal noise ratio, which is almost the same thing as what we discussed earlier. In conclusion, we obtain a conjugate gradient parameter from spectral CG direction in such a way that the sufficient descent property holds without line search consideration. And the algorithm is used to solve robotic model problem and image restoration problem respectively. The paper we use for details of what we discussed this afternoon, you can find it through in this paper just published March this year. Thank you for listening.
Okay, any question or suggestion? Don't have question? Okay. Okay, Sunny, you can.
Okay. Thank you very much, Doctor, for thank you very much for this presentation. It's really interesting. I'm curious, what motivated you to come up with this parameter that actually improve the performance based on the existing result?
In response to the question, actually, the motivation behind this work is the additional burden attached to beta K R male by die. That is this relationship 9. If you observed, there is a cost for computing this relationship, which is which is backbone of this method. Before we show the convergence of this method, we must have this relationship. So we now observe that even without this relationship, we can still have the global convergence or convergence of beta K R male without that burden attached to it by die. So that is the major motivation behind this formulation.
So is this the same beta K you use?
No, I did not use the same beta K, but in the south direction, there is a little modification on the south direction. The south direction used by this, it assumes that the parameter theta K here is equals to 1 instead of equals to some relationship. So that's actually what, if you observe, our new theta K we obtain is given by 13. So the only difference between our old method with the previous RML versions is that this scaling parameter we introduce in order to have a nice convergence property.
I believe it has to be with the gradient as well.
Yes.
Isn't also this one costing, isn't it like potentially cost because you need to know about the number of media and the number of using here make some decisions and then including the cost figure the time. What do you think about the figure several test functions and you realize that only the computation of this is not as fast as the computation of that function.
Actually, if you observe, since we have norm, we are good to go because whatever we obtain here, we know that this is not going to 0. That's first. So unlike what we have in the burden attached to this parameter by die, whereby there are some instances whereby some test functions may violate this rule. So based on that, we know that definitely our new method will perform better than this method because it almost solves all the test functions without violating some of the test functions there. Go back to this is the beta K we use instead of this. They use this in most of the RML versions later than this. This is what they normally use in computing. So we use the original beta K RML.
second one idea of possibility of X being negative at all. Right?
Yes.
So there is no ability to do it.
You said? Yes. Thank you, sir. Cool. Now she go sit near doctor.
Yeah, finished, right?
Sabida wannan evaluation ne maki zai assign. But this one is for lab, so we practice, so we ask all questions that they are not clear for us. Me kake son sa?
Can I share my screen? Hello? Hello?
Yeah, yeah, you can. You can start.
Okay, can I share my screen now?
Yeah, yeah, yeah.
Okay, everyone, can you see my screen?
Yeah, I see.
Okay. Let me introduce myself that it's me, Saqib Murtaza. And today I am here to present my research article, and the title of the research article is Fractal Fractional Analysis of Nonlinear Electroosmotic Flow with Cadmium Telluride Nanoparticles. It's a presentation layout. First, we will discuss research background of the present study. Then we will shift to the literature review. And on the basis of literature review, we found some gap, and then we propose our model, and we will study the novelty of the present study. Then we will move to the objective of this study. Then we discuss significance of the present research article, and we will discuss in the next session modeling and results. And we will summarize our articles with some concluding remarks, and then I will share some future direction, then how can we extend this article. So let's start from the research background. In the research background, we will discuss some basic terminologies that are the part of the present research work. So the first one is fluid dynamics. Fluid dynamics is actually the study of fluid's motion and its behavior. And we have many applications of the fluid dynamics, but here we have few of them that are ocean tides, weather patterns, air conditioning system, and wind turbines. In fluid dynamics, we use many equations, but here we have some fundamental equations that are Navier-Stokes equations to study fluid flow behaviors. For heat transfer in the fluid dynamic system, we use Fourier law of heat conductions, and for the concentration of the particle and mass distributions in the fluid equations, we use the Fick's law equation. The second basic term is fluid, and fluid is a substance that deforms continuously under the applied shear stress. And on the basis of Newtonian law of viscosity, we have two categories of the fluids. The first one is Newtonian fluid, and the second one is non-Newtonian fluids. Now, those fluids which obey Newton's law of viscosity, we called it Newtonian fluid, and those fluids which do not obey Newtonian law of viscosity, we call it non-Newtonian fluids. Newtonian fluids, Newtonian law of viscosity are referred to that when we have linear and direct proportions between the shear stress and shear strain, we called it Newtonian law of viscosity. We have some example of the fluids that are water, air, paints, honey, and oil, etc. We have different types of oils in the industries for many purposes, but one of them are the diathermic oils. Diathermic oil is also known as thermal oil, which is a type of heat transfer fluid that is used in industrial applications to transfer heat between a heat source and a heat sink. It can operate at a higher temperature without boiling or freezing. In our study, we considered one of the example of diathermic oil, that is engine oil. So therefore, I explained it here. Nanofluid is a heat transfer fluid that contains nanometer-sized particle. Choi and Eastman were the first researchers to prepare the nanofluids in 1995 at Argonne National Laboratory. According to the literature, we have different types of nanoparticles that are bricks, spherical, cylindrical, and platelets. And each of these types has their own features and thermophysical properties. On the basis of number of nanoparticles in the base fluids, we also have different types of nanofluids. The first one is unary nanofluid that contain only one nanoparticle. The second one is binary nanofluid that contain two different nanoparticles. Ternary nanofluids are referred to those fluids which contains three different nanoparticles, and so on. Now, the very basic term and topic of our present research work is fractional derivative. Fractional derivative is the generalization of classical derivative in terms of its order. Fractional derivative contain the non-integer order derivative of the function, and its history related to the very famous letter that was written in 1695 from L'Hopital to Leibniz about the order of the derivative. Leibniz responded that it is apparently a paradox, but in the near future, we will get some fruitful consequences. But why fractional derivative? It is recognized by many researchers that fractional calculus is an efficient tool to describe complex and real-world problems, including viscoelastic material, fluid flow, diffusive transport probability, electrical networks, and electromagnetic theories. From 1695 to till now, we have so many fractional derivative operators in the literature, and each of them has their advantages and drawbacks. But there are, I'm going to mention a few of them that are most used in the literature till now. They are Riemann-Liouville fractional derivative, Caputo fractional derivative, Caputo-Fabrizio, Atangana-Bellino fractional derivative. And now we have the recent one that is the combination of two different derivatives, that is fractal fractional derivative. From the present research analysis I have gone through many research articles which are related to mind study. But here I will mention to the base papers which I studied, and then I extended these papers. Sheikh et al. Discussed fractional model of Casson nanofluids with the impact of cadmium telluride nanoparticles. Murtaza et al. Analysis numerically the fractional of Casson fluid flow in microchannel. And in another study, Murtaza et al. Examined the fractional model of Casson fluid flow along with electroosmotic effects. So keeping in view the mentioned research article, we found that no one has considered the fractional model of Casson nanofluid flow with cadmium telluride nanoparticles and electroosmotic effect. The present research work is novelty on the basis of these few assumptions. We have considered fractional models with nonlinear PDEs. The nanoparticle has been considered, that is cadmium telluride nanoparticles. The electroosmosis effect and the viscous dissipation effect also has been considered in the present study. And the problem has been solved by a Craig-Nicholson scheme. Here we have objective of the study. To formulate and obtain the numerical solution of natural convection flow of Casson nanofluid flow. To show that fractional model describes the flow behavior better than the classical model. To explain the behavior of embedded parameters on the generalized Casson nanofluid velocity, temperature, and concentration. to study the application and general uses of Kesson nanofluid in modern technology, and to show the rate of heat and mass transfer of regular fluids by adding nanoparticles in them. These are some significance of the present study. The result obtained from their research, this research will help to enhance the knowledge of fractal frictional model and nanofluid flow. A base for complex nonlinear flow problem recurrently taking place in engineering and applied sciences, understanding physically trends and feature of various nanofluid flow. And this article will help. Fractal frictional models will provide deep study about the rheology of fluids flow as compared to the frictional and classical model. Here we have a research methodology that we adopted in the present research articles. Primarily, we proposed a problem. Then we model it mathematically with initial conditions and governing PDEs and boundary conditions. Then we make it non-dimensional by using some non-dimensional parameters. After non-dimensionalizing, we make them generalized by using the fractal frictional approach. After generalizations, we discretize the model by Frank-Nicolson schemes. And then we draw the results, the graphical results for the embedded parameters, and then we sum up our final result with the concluding remarks. The next section is about problem formulation. Here we have the geometrical illustration of the problem. The geometrical illustration of the fluid phenomena is in this slide. From fractal frictional electrosmotic Kesson nanofluid flow has been assumed in a micro channel of length L. At T equal to 0, the fluid and plates are assumed to be static with an ambient temperature and ambient concentration. But at the time greater than 0, the left plate is disturbed with the velocity of magnitude u sine omega t, which transmits the motions in the fluid, while at the same time the temperature and concentration of the fluid are rise to time-dependent temperature and concentration. These are the velocity, thermal, concentration, electric, and magnetic field, which we will use to develop our governing PDEs. These are the base equations by which, with these equations, we have modeled our problems. The first one equation is Navier-Stokes equations. In the Navier-Stokes equations, rho BF is actually the body forces. And in the third equation, J cross B is actually the magnetic field, which has been derived. The final expression has been derived with the help of generalized ohmic law. These are the nanofluid correlations to model the problem. All of these equations we have used just to model the governing equation. Equation 7 represent velocity equation. Equation 8 represent heat equations. Equation 9 represent concentration equation. These are the initial and boundary conditions. These are some dimensionless variables which we will use to non-dimensionalize the governing PDEs. These are a set of dimensionless equations. Equation 12 represent momentum equation. Equation 13 represent energy equation in non-dimensional form. And equation 14 represent mass equations in non-dimensional form. These are dimensionless initial and boundary conditions. During dimensionalization process, we get some dimensionless parameters. The first one is Grashof number. The second one is mass Grashof number. The second one is magnetic parameter. The third one is Prandtl number. And the last one is Schmidt number. Now here we generalize our model by using the fractal frictional operator. And when we use the fractal frictional operators on equation 12 to 15, we get these three equations that are in generalized form. This is the expression for the fractal frictional operator. These are the discretization form of the first order fractal frictional derivative. The first and second order derivative of the functions can be discretized by using Frank-Nicolson scheme, which are under, we have equation 22 and equation 23. Using the above address discretization given in equation 21 to 23, the fractal frictional order governing equation will take the form. This is momentum equation. This is energy equation.
Yeah, you need to redefine.
And this one is concentration equation. Now this is a result and discussion section. Figure 2 represent the comparison between fractal, and classical model behavior. Figure shows that fractal model has greater memory impact than the fractional and classical model. This feature of the fractal model is due to the extra fractal dimension. Because of the higher memory impact, the fractal model is more realistic and applicable to real world situation. Moreover, the fractional parameter allow experimentalists to compare their experimental work with one of the best suited layer. On the other hand, we have figure 3 that has been drawn to change in the velocity field in response to the dispersion of cadmium telluride nanoparticle in the fluid. From the figure, it can be easily analyzed that as the concentration level of cadmium telluride nanoparticle increases, the viscous layer in the fluid becomes strengthened, and due to this strengthening in the viscous forces, the fluid motion retard, and we observe decay in the velocity profile. Figure 4 has been plotted for the influence of the Casson fluid parameter on the fluid's velocity. From the figure, it is very clear that the increasing magnitude of xi increase the fluid's motion in a microchannel. This increasing trend in the velocity field is due to a decrease in the viscosity of the fluid. As the Casson parameter increases and approaches to infinity, then Casson fluid converted to a non-viscous fluid with a zero viscosity and its velocity boost up. Figure 5 reveals the upshots of asymmetric zeta potential on the velocity field. Zeta potential of the plate is related to the magnetic charges in the fluid. So by increasing the magnitude of zeta potential, the magnitude of the drag forces in the fluid enhances, with which consequently thins the electric double layer, and as a result, fluid moves fast. The impact of thermal Grashof number GR on the velocity field of engine oil has been plotted in figure 6. Increasing behavior can be seen from the figure for increasing value of GR. Physically, this trend is true because the greater magnitude of GR weakens the viscous boundary layer of the fluid and produce buoyancy forces in the fluid. So due to these effects, the fluid motions accelerate. The impact of magnetic parameter M on the velocity profile has been drawn in figure 7. Decreasing profile of the velocity has been noticed for a larger value of M. This result is quite clear because increasing value of M generates drag forces. We also called it Lorentz forces in the fluid, which retards the fluid motions, and as a result, decreasing trend in the profile of velocity has been observed. Figure 8 shows the change in thermal energy distribution in response to the volume fraction of cadmium telluride in nanoparticle in engine oil. This sketch indicates that when the amount of cadmium telluride nanoparticle increases, the thermal field exhibits rising variation in the profile. This effect is caused by increased strength of the viscous forces in the fluid because of the addition of cadmium telluride nanoparticle to the engine oil. Figure 9 depicts the effect of KMUTT numbers on heat transfer. The temperature profile shows a rising trend as the magnitude of EC increases. This is physically valid since KMUTT number denote the ratio of boundary layer kinetic energy to its enthalpy difference, because a positive KMUTT indicates a heat transfers from the plate to the fluid. Increasing dissipations of viscous heat result in a rise in the fluid's temperature. The behavior of concentration profile in response to the volume fraction of nanoparticle in conventional engine oil is depicted here in figure 10. Figure 10 shows an increasing shift in the concentration profile in response to greater value of phi. This is because greater value of phi increases the degree of viscous forces in the fluid, causing the concentration profile of the fluid to rise. It's a very important table of the present study, which consists two things. The first one is Nusselt number, and the second one is Sherwood number. Table 2 present variation in heat and mass transfer against volume fractions. Table 2 reveals that increasing value of volume fraction, heat transfer increases while mass transfer decreases for larger value of volume fraction phi. From table, heat transfer enhances up to 15.27% by adding 4% of cadmium telluride nanoparticle in the regular engine oil, while on the other column, we can see that mass transfer decreases up to 2.07% when adding 4% of cadmium telluride nanoparticles are added in the base fluid. Now we will summarize our present work with the concluding remarks, and here we have some key findings. In comparison to the fractional order and the classical model, the fractal fractional has a strong memory effect. The fractal fractional model has these characteristics because of the extra fractal parameter, which is absent from the fractional and classical model. The fractal fractional model is handier and more realistic to the real world phenomena due to the higher memory effect. Against greater value of Casson fluid parameter, thermal gray shift number, and zeta potential, the velocity profile enhances, while shows opposite trend for the magnetic parameter and volume fraction of the nanoparticles. Against greater value of phi and Eckert number, temperature profile enhances. For greater value of phi, the concentration profile enhances. When the magnitude of volume fraction reaches up to 4%, the rate of heat transfer increased with the rate 15.27%, while mass transfer rate decreased with 2.07%. Here I have some future suggestions to extend the present work. We can change the geometry, and we can consider cylindrical coordinate system or polar coordinate system, spherical coordinate system, thin needle. We can also consider to extend this present work. We can also change a different type of fluid. We can consider if we can change the boundary conditions, so that then we can also extend. And by changing some nanoparticles, we can also extend this present research works and relate with the industrial and engineering applications in the future. Thank you very much.
Yeah. Nice presentation.
Any question?
Thank you. Now, if anyone has some suggestions, I will request that you can suggest me for improvement of the presentations. Or if you have any questions, you are welcome.
Thank you very much. May I ask a question?
Yes, yes.
Yes. Thank you very much.
Everyone is
presentation.
Yes.
You know, I'm not into this kind of problem, but I'm interested in it. Probably in the future, I may consider such a situation of dynamical systems in general. So, what I would like to ask is, how do you come up with your model?
Actually, we studied the importance and significances of two things. The first one is fractal fractional derivative. That what are these derivatives and what are the significances when we apply these models on our fluid dynamic systems. And the second thing that we actually studied the nanoparticle significances. And in the literature nowadays, we have many different types of nanoparticles, in which I selected the cadmium telluride nanoparticles, and then I studied that what are the importance and what it will be the heat transfer rate when we use this into the diathermic oils. So after all of these studies, then I concluded that I have to model my new mathematical governing equation, and that I models, and then I present in front of all of you. And this research article is actually published in the last month in Scientific Report.
Yeah, can you show it on the slide, please? Because I cannot see this.
I'm looking. Let me stop this screen and then I will share again.
Oh, okay, thank you.
I don't know what happened here. Yeah, now you can see the screen, Mr. Sunny?
Yes, I can see.
Okay, I will go to the literature review. You can see here, I studied a lot of paper, almost 10 to 15 research articles I studied. But here I just mentioned 3 research articles, which are the fundamental, or we can say the base research articles, just to develop the new model. See, in the first paper that is published in 2021, Nadeem Ahmad Sheikh and Dennis Link, studied the fractional models of the Kesson fluid, and they used cadmium telluride nanoparticles. They used the generalized Fourier's and Fick's law to model their equation, and then they studied the impact of cadmium telluride nanoparticle with the fractional models. Okay, that was the first paper which I inspired, and then I studied about the cadmium telluride nanoparticles. Now, second and third paper, you can see here in the second paper, this is mine paper that is actually I published in 2022. That consists only the fractional model of the Kesson fluid with exponential memory impact. This is a very, you can say a small model, because it was very new topic in 2022 to study the fluid models with the fractional derivative. And then I extended my own work in 2022, and I generalized them with the electrosmotic effect, and I studied, I considered the microchannel in my own study, and I extended. So on the basis of these three papers, and I combine all these three papers, cadmium telluride nanoparticle, fractional derivative, electroosmosis effect, and non-linearity in my model. So then I came to my new research topic, and I model it. So these are some, you can see the topic which are very new in my research work. This is novelty. I have fractional models, non-linearity, cadmium telluride nanoparticle, electroosmosis effect, viscous dissipations, which is non-linearity, and Craig-Nicholson scheme. So these are the things which are very new in my research work.
Can you show us the governing equation?
Yes, I can show. Yeah, these are the governing equations actually here we have on the screen. You can see the first one is, velocity equations, which we have derived from the Navier-Stokes equations on the basis of our assumptions. The second equation, that is heat equations, and we developed these equations with the help of Fourier law of heat transfer. And the second, that is concentration equations, which we developed or formulate with the help of Fick's law of concentration particles.
Yeah, my curiosity is actually how you were able to incorporate all those what you call novelty.
Actually, let me explain
this particular equation. As a layman, please, can you explain to me?
We use in fluid dynamics system, that is we have on this slide. This is Navier-Stokes equations. Whatever research article in fluid dynamics you consider to study, all of the governing equations in the fluid dynamics paper is actually derived from this main equation. This is only one equation, that is we call Navier-Stokes equations. Okay, this is in very simple form. You can see in the first equations, the first term that is considered total derivative. The second one is actually the tensor, okay, gradient of tensor. And the third one, or the last term, that is we have the body forces. Now this is up to you. What are your assumptions? What are your considerations? You can consider, and then you can mathematically model it, your assumptions, and then you can incorporate in these equations. So you need to have lots of calculations in your base equations. So then you will reach to the final governing equations. But the base equations you have to need, this is the only one equations. You have to need to understand this equation.
Oh, is that for every nanoparticle?
No. Nanoparticle is something else. I'm talking about the fluid dynamics governing equations. Nanoparticle comes after when you develop your fluid governing equations.
Okay. I see.
For the nanoparticles, let me clear to you. Once you have modeled this equation, okay, you can see the velocity equation. Here you can see in the subscript NF. You can see with the row with In a regular equation, by regular equation, we mean that when we don't have any nanoparticles, okay? In the regular equation, we don't have this subscript, okay? Yes. But when you consider the nanoparticle in your fluid system, then you are restricted that you have to write this NF just to show that now this density is for the nanofluid, not for the regular fluid. And we use these equations. These are the nanofluid correlations. You can see here.
Oh, so
And
these correlations are existing in the literature.
When you go for the literature to study these type of correlations, so you will find many of them. Now this is about your consideration that which particle you have used. Either this is spherical, either this is brick, either this is platelets, either you consider a non-linear models. So this is your assumptions. This all depend all on your assumptions, which model you have exists and which you have to study.
Oh, okay. Thank you.
Welcome.
Finally, is there any text where one can find all these correlation related to nanoparticles?
Very soon, in the almost after 2 days, Dr. Talha Anwar will present a topic in the workshop that is in Pattaya, that is about review on the nanofluids. Okay, so I hope it will help you that how you can select or how you can study these nanofluid correlations. Now on the screen, you can see the nanofluid correlation that I choose from the Tiwari and Das models. I will share a paper with you, but you cannot find all these correlation in one paper.
Okay. Thank you. Sir.
Welcome. Any question from the audience, please?
Okay, if no any question and suggestion, thank you for your nice presentation, Sakib.
Welcome.
Okay, today we finish for individual presentation. Everyone,
Can I stop
please
my
turn
screen?
on. Yeah, you can stop your screen, and everyone please turn on your camera. พี่อีฟค่ะพี่อีฟหนูฝากแคปหน้าจอให้หน่อยได้ไหมคะได้แป๊บนึงนะได้ค่ะ
Dr. Talha पे जरा help करवा देना सनी की
मेरे तो चंगी पाई है
हाँ ना बड़े होने आप
ठीक है तो सही गल है
เพชรลาพร
हम भी कुछ सीख लेंगे
lab here are you in the lab
ถ้าช้างแล้ววันนี้เรา
I'm in my home
what is that me
He's in the lab. He represented me well already. So what are you asking?
พร้อมยังอ่ะ
อะไร
โอเค
You are also me.
everyone take picture นะ one two three
So he represented you
okay
already.
one more time one two three okay ขอบคุณค่ะพี่ thank you everyone see you on next day okay bye bye see you
Okay, everyone. See
Okay.
everyone.